Good morning, everyone. My name is Manuel Algaba. I come from IQM Quantum Computers in Germany, and I'm also a PhD student at the Autonomous University of Madrid. And today I will be presenting the second part of this talk called Simulating Nanoscale NMR Problems on a Co-Designed Quantum Computer. So first, I will show you an overview on co-design strategy, then its implementation for our specific problems, and finally, some results that we got. So what is co-design? Co-design is mainly about tailoring your hardware and your software towards your specific problem instead of choosing a more generic approach for every problem. So this way we can make the most of our quantum computer. The problem was already introduced by my colleague in his first talk and also the simulation algorithm. And now I will talk about the swap routing and how to optimize these swap gates through the use of a specific architecture. In a separate talk that was already given, another colleague showed the hardware implementation details for this architecture. So the problem we will consider was already introduced by my colleague in his talk, but we can remind it had a nuclear-nuclear interaction term in its Hamiltonian. So we can have two cases regarding this. We can either non-include it, so we would have the non-interacting case, or include it, so we would have the interacting case. In the non-interacting case, we have an NV center in the middle interacting with the carbon-13 nuclei in the surroundings through dipole-dipole interactions, and they are also embedded in a microwave radiation driving field. So we can use these interactions to send some polarization to the carbon-13 nuclei in what is called the hyperpolarization protocol that is useful, for example, for medical imaging. So we want to simulate this system to find the optimal operation parameters of this driving frequency. In the interacting case, we could have a little bit more accurate simulation because of these interactions that we are including, but they are not so important as the NV center nucleus interactions. So sometimes they can be neglected. But if we want to simulate these using a more standard approach, we could, for example, use a square grid. Since this is not an all-to-all connected chip, we would require a swap routing or to insert some swaps around to be able to perform all those interactions that are not natively present in our chip. For the non-interacting case, we can study the numerical techniques and represent the number of swaps that we require for this problem using these numerical techniques for the swap routing. So we see that they scale very nice, but still we want to make it better because we want to compare this square grid performance against the co-design chip performance that I will show you later. So first of all, to show you the co-design chip, let's focus on the square grid and how we can outperform these numerical techniques. So let's imagine we don't have a square grid, but indeed a linear chain embedded in it, or a linearized square grid. This way, we can just neglect the connections that are not present in this linear chain, even though they will still be in the chip. And now we can focus on a piece of this linear chain. We label the qubits 1, 2, 3, 4 for the nuclei, and the 0th qubit will be the NV center. Now we can perform the interactions of the NV center with the neighboring qubits and swap around with the following qubit. Now we can perform the new interaction that is able, and we can swap around with the next qubit and do this until we find the desired interactions have been performed. So if we look at the previous graphic, we can see that we will improve this because now we have a linear number of swaps and a linear depth. And if we plot this here, we can see that we outperform all the previous numerical approaches. Once that we have shown that the best case we can find for this square grid simulation, we can focus now on the co-designed chip. For that, let us study the structure of our problem, and let's try to place also, as here the NV center is in the middle, let's try to place a qubit representing the NV center in the middle, and let's surround it by qubits representing nuclei here. We can see that all the interactions now can be done natively, and thus we need no swaps, and the depth will still be linear. So we have shown that the co-design chip can perform better for the non-interacting case and the square grid. But now let's focus also on the interacting case, where we have an all-to-all simulation. So for the square grid, let's use the odd-even sorting that starts with doing all the neighboring interactions between qubits. Then we can just swap around the odd qubits with the ones on the right. And now we can perform again all the neighboring interactions and again swap around, but now the even qubits with the ones on the right. If we keep doing this, we will find the desired interactions have been performed in a quadratic number of swaps and in a linear depth. So if we study this interacting case for our co-design chip, even though it's not meant to be optimal here because it's designed for the non-interacting case, we can still find that outperforms the square grid in terms of the number of swaps. So here we can just do all the interactions, then we swap around with the next qubit, and we do the remaining interactions here and swap around and do this until we find the desired connections and interactions have been performed. This way we can achieve that simulation in a linear number of swaps. So we have improved the swaps from quadratic to linear compared to square grid, but the depth is quadratic and in the square grid was linear. So if we now study the percentage of saved swaps by using co-design instead of square grid, we can see that for the non-interacting case is 100% because we were including no new swaps. But for the interacting case, it's still really nice because we can save up to 90% of the swaps by using 20 qubits, and it keeps growing. So co-design in general can perform better than square grid for this specific problem and just for the number of swaps. So how is this translated to the real results we can find on a quantum computer simulation? Well, this graphics was already shown by my colleague in his talk, and here we can see the polarization in the y-axis of each nucleus for a range of different frequency for the microwave driving we are sending to the sample. And we want to obtain some information about these peaks. So let us focus on one of them. The solid line will be the behavior that we can find in nature, while the dotted line is the simulation result we obtain from a noisy quantum computer. They have different parameters, and we want to study how the performance will be in the co-design chip against the square grid. So we will study two benchmarking functions mainly. The first of them will be this psi rate, in which we fit a Gaussian peak here in this peak, and then we study the height of this Gaussian peak against the variance of this Gaussian peak. So this is that ratio, and we average over all the nucleus peaks that we can find. So if our simulation has more noise, then the peaks will be flattened and we will obtain smaller psi. So this way, simulation will have a higher psi. And also the second benchmarking function will be this peak frequency error, in which we just study how much we are misplacing omega ideal by choosing these omega noises that we can obtain from our noisy quantum simulation. So if we see the plots, we can see that co-design will outperform square grid for the psi rate against the square grid for a range of 2 qubit gate errors, and will approach ideal case. For the peak frequency error, we can observe the same. The ideal case would have 0 peak frequency error, and co-design is closer than square grid to this case. So if we study the state-of-the-art parameters, we can see that we can improve both quantities by a factor of 3 by using co-design. And indeed, in this case, we can obtain the same results than square grid by using a 2 qubit gate error that is 1 order of magnitude worse in the co-design approach than in the square grid approach. So we can extract from here 2 main things. First of them is that tailored chips can perform better for specific problems, but also that reducing gate errors is not the only way for pursuing quantum advantage, because we can use these co-design approaches in which we reduce the required resources for achieving some results just by tailoring our quantum computers to a very specific problem. So thank you for your attention, and if you have any question, I'd be delighted to answer. Thanks.